In part B of our problem now, it says find expression for the total energy supplied by the battery as the capacitor is being charged. So as the capacitor gets all charged up, how much energy is supplied by that battery? So let's start with what we know. We know that power is current times potential. We know the potential is epsilon, so we need an expression for our current. So to start part B, let's use our expression for charge and get an expression for current. And what we know is that current is the change in charge over the change in time. So that's going to be our Q maximum times the derivative with respect to time of 1 minus e to the minus t over tau. So that's Q maximum. The derivative of 1, of course, is 0, minus the derivative of e to the minus t over tau is minus 1 over tau e to the minus t over tau. When you take the derivative of an e term, you get the e term itself times the derivative of what's in the exponent. And then we'll close our brackets. Equals Q maximum divided by R times C, remember tau is R times C, e to the minus t over tau. There's an expression for our current. We can use this expression for current now to find an expression for the power supplied by the battery. So the power supplied by the battery is current times potential. Well, what we see that we have up here Q maximum, let's just deal with this a little bit further. So our current is Q maximum over R times C e to the minus t over tau. That's all going to be multiplied by our potential epsilon. Q maximum is the maximum charge on the capacitor. We had that in our previous expression. That was epsilon times C. So our C's cancel and we've got epsilon over R left. So then that gives us epsilon squared. Epsilon times epsilon is epsilon squared. We've got our R in the denominator. Then we've got our exponent term. Okay, so there's the power of the battery supplied as a function of time. What's the total energy supplied by the battery? Well, let's remember that power is change in energy over change in time. So then change in energy is power times change in time. So then our total energy would be the integral of du. So 0 to u equals the integral of power over time. Let's fill in what we have next. So then the integral of du is just u. Got the integral of our power, epsilon squared over r, e to the minus t over tau. To get the capacitor to the full charge, the total energy supplied by the battery, we'll take our time from 0 to infinity. So epsilon squared over r comes out front. The integral of e to the minus t over tau will be minus tau times e to the minus t over tau. And that's going to be evaluated as t goes to infinity and at t equals 0. So let's put in the limits of that integral next, and then we'll get the total energy supplied by the battery. So the next part we have is our potential energy is epsilon squared over r times minus tau, so minus r times c. And then we want e to the minus t over tau evaluated our limits. So that's 1 over e to the t over tau. This guy, as t goes to infinity, must be 0. Minus 1 over e to the minus 0 over tau. This guy is equal to 1, plus 0 over 1. That guy is equal to 1. We get epsilon squared over r times minus rc times minus 1. Let's see, those r's cancel. Minus times minus is plus, and we get epsilon squared times c. There's the total energy supplied by the battery, and that's our answer to part B. Next, in part C and D, we'll find the energy dissipated by the resistor and the energy stored on the capacitor.